land like this. Instead of the usual way like this. But this airplane should fly like this, as fast and as economically as a conventional airplane. Many people have offered many solutions to the problem. The VSTOL era of aircraft, with vertical rising, hovering, and high-speed flight capability, moved closer to actuality early in 1964 as the Ryan Aeronautical Company unveiled the world's first lift-fan research aircraft, the XV-5A. This unique aircraft was designed and built by Ryan for the United States Army Transportation Research Command, under contract to General Electric, developers of its lift-fan propulsion system. The XV-5A is supported by many years and several million man-hours of study and actual hardware experience by Ryan in developing revolutionary new vertical and short takeoff and landing aircraft. Among the remarkable predecessors to the XV-5A was the world's first pure-jet VTOL aircraft, the Ryan X-13 Vertijet, first flown in 1957. In 1955, Ryan engineers had begun work on a new concept, the fan-in-wing type airplane, Vertifan. And in 1957, Ryan was awarded an Air Force study contract to apply the Vertifan concept to military requirements. Instead of the larger, heavier, more powerful engines normally required for vertical flight, with their attendant weight penalty and higher fuel consumption in horizontal flight, the Ryan Vertifan design calls for power plants sized only for cruise and range requirements. To meet the power requirements of vertical takeoff, hovering, and landing, the basic thrust is multiplied 300% through fans installed in the wings and fuselage. The U.S. Army Transportation Research Command awarded General Electric and Ryan the contract to design and build two XV-5A research airplanes in 1961, although studies directly associated with the aircraft were underway in 1959. More than 600 hours of wind tunnel tests with 5 different scale models, including 340 hours with a full-scale propulsion system, proved the effectiveness of the XV-5A's basic design. Flight operations from takeoff through transition were simulated at speeds from 0 to 120 knots, with lift fans operating up to full power. At the Ryan plant in San Diego, an XV-5A mock-up was built for engineering design confirmation and inspection. As fabrication of the two flight aircraft proceeded, interest was focused on the unusual fan-in-wing arrangement. This unique propulsion system consists of 2 GE J85 turbojet engines mounted high in the fuselage, 2 5-foot diameter fans submerged in the wings, and a smaller fan in the nose just forward of the cockpit. By the use of diverter valves in the tailpipe, the thrust from the engines can be channeled to the fans for VTOL operation or out the tailpipe for conventional flight. The first of the 2 XV-5As was shipped by truck from San Diego to Edwards Air Force Base in February 1964. Within weeks, the second airplane was sent to the NASA Ames Research Center for wind tunnel testing. At Edwards, high-speed taxi tests were started in preparation for the first conventional flights soon to follow. But let's go back and examine the 2 decades of experience that led to these flights. Ryan's VSTOL research actually began nearly a quarter century ago when the Army Air Corps sought a short-range observation plane for use from small, unprepared fields. Ryan's answer was the YO-51 Dragonfly, a two-place single-engine high-wing monoplane, which required less than 50 feet for takeoff and landing runs, and appeared almost to hover in certain conditions. Partly responsible was the tremendous area of the 52-foot wing, which had flaps so broad that they represented, in essence, a retractable wing. During World War II, Ryan produced the first tactical fighter for the Navy with a jet engine, a unique aircraft with a piston engine forward and a jet engine aft, the famed FR-1 Fireball. At a near-empty fuel condition, the Fireball's combined thrust was nearly equal to its weight. Ryan engineers began to realize that ultimately a jet propulsion system would be developed to produce thrust in excess of aircraft weight, making vertical takeoff possible. This led to informal studies of the possibilities of jet-powered VSTOL aircraft. In 1947, the Navy awarded Ryan a contract to explore the feasibility of reaction control for jet aircraft. A simple steel framework provided support for a conventional jet engine, a tailpipe, and the remainder of the jet reaction control system. On May 31st, 1951, the lightly tethered rig made the world's first free hovering jet flight by remote control. The test vehicle took on the shape of an airplane, as the simulated delta wing was added and a crude cockpit was built atop the engine. In 1953, Ryan test pilot Pete Girard climbed aboard and made the world's first piloted hovering jet flight. The first X-13 Vertijet arrived at Edwards Air Force Flight Test Center in the fall of 1955. In more than 120 demonstration flights, the X-13 exhibited the precision and reliability of jet reaction controls and the Ryan-developed automatic stabilization system so successfully that one observer referred to this demonstration as the Vertijet Ballet. In a spectacular public demonstration at the Pentagon in July 1957, the X-13 amazed civilians and experienced military observers alike with a full-cycle transitional flight. Another VSTOL concept, the deflected slipstream principle, was studied by Ryan and successfully demonstrated by the VZ-3RY vertiplane. Built by Ryan for the Army and the Office of Naval Research in the late 1950s, the vertiplane uses large retractable flaps to deflect the propeller slipstream downward to provide vertical lift for takeoff, hovering, and landing. The flaps are retracted for conventional horizontal flight. Recently unveiled, the XC-142A tilt-wing transport is the world's largest vertical takeoff and landing aircraft. A three-company team effort, Ryan, Vaught, and Hiller, the XC-142A is designed to carry 32 combat-ready troops or 8,000 pounds of cargo 200 to 300 miles at speeds up to 350 miles per hour. The wing can be tilted through an angle of 100 degrees, enabling the plane to take off and land vertically, hover, and even back up. Ryan's assignment in the XC-142A project is construction of the aft fuselage sections, wings, empennage, and engine nacelles. 5 tactical cargo aircraft are being fabricated for operational evaluation, the first such military program to reach this status. For short-field takeoff and landing requirements, Ryan has developed an entirely new family of aerial vehicles utilizing flexible materials for aerodynamic support. The Ryan flexwing was tested in a manned test bed using a membrane of flexible plastic-coated material attached to a keel and leading-edge members to form an arrow or V-shaped wing surface, offering an extremely lightweight, large aerodynamic lift surface. This vehicle evolved into the XV-8A Fleep, a manned flying truck with a takeoff distance of less than 300 feet, a 1,000-pound payload capability, and a 100-mile range.
Here is one of the most unusual and significant airplanes in the world today, the United States Army's XV-5A VSTOL research aircraft. It was designed and 2 aircraft were built by Ryan Aeronautical Company under contract to General Electric, developer of its lift fan propulsion system. Though it looks conventional, it is full of surprises. There is little about its sleek appearance to suggest its unique capability to take off vertically, hover, transition to high-speed horizontal flight, and land vertically. In fact, it is this capability, operation in rugged terrain from unprepared areas, for which it is specifically designed. The most remarkable thing about the XV-5A, without parallel among VSTOL aircraft, is that no more basic power is required for vertical flight than for conventional operation. Only the lift fan eliminates the penalty of installing, just for VTO, far more power than is needed for normal jet flight. How is this possible? The outstanding efficiency of the Ryan Vertifan stems from a new thrust conversion system. When jet engine exhaust is diverted from the normal tailpipe to spin rotor-like fans within the wing and nose, the resulting thrust is multiplied threefold. Relatively small quantities of high-energy exhaust gases are used to drive the fans, which in turn pump large quantities of low-energy, large-mass flow air through the fan system. The fans are like multi-bladed airplane propellers, in this case accelerating the air directly downward to lift the plane vertically. In this concept, the same basic power output serves the entire range of flight modes, hovering to maximum speed. Power and fuel required are the same for vertical flight and hover as for conventional high-speed cruise. The stability of the XV-5A, even close to the ground during vertical takeoff and hovering, has been outstanding, and no tether tests were necessary before the first liftoffs. Maneuverability with precise control has been remarkable. The XV-5A is under positive control by the pilot throughout all flight regimes and stable about all axes. Louvers beneath the fans are vectored to provide directional and roll control. The airplane can easily be translated backward, as well as forward and sideways. Control harmony is excellent. Because of the relatively slow, cool downwash of the vertical lifting fans, operation from unprepared surfaces is practical. Until they have flown the XV-5A, pilots find it difficult to believe that it is so easy to fly an airplane which combines the advantages of a helicopter and a conventional jet aircraft. It's far easier than flying a helicopter, is their usual comment. Official United States Army acceptance flights have demonstrated the great potential of the lift fan concept. As a switch is actuated, fan doors are opened for the vertical flight mode. During liftoff, the pilot controls rate of ascent by a collective lift stick, similar to a helicopter. Conventional stick and rudder pedals are used for the other controls in both flight modes. For hovering flight, the XV-5A uses the basic thrust of its 2 GE jet engines channeled through a ducting system to the plane's wing fans and a nose fan. The latter controls the airplane in pitch. The plane lifts off effortlessly with no forward speed and can fly straight up as high as necessary to clear surrounding obstacles. The atmospheric air drawn through and accelerated by the fans has many times the lifting power of the jet thrust alone. No other VSTOL concept offers this degree of thrust augmentation. The fans provide forward velocity when the louvers beneath them are deflected. The Vertifan has the vertical flight capabilities of the helicopter, combined with the high performance of a fixed-wing jet aircraft, doing both jobs efficiently without compromise. The landing gear is retracted, and when the 90-knot speed needed for aerodynamic wing-supported flight is reached, a diverter valve shifts the engine thrust from driving the fans to the tailpipe. Conversion from fan mode to conventional jet takes less than 1/10 of a second. In this configuration, the louvers and the butterfly doors above the fans are closed. This research aircraft has flown at over 400 knots, but the basic vertifan design lends itself to a speed spectrum of 0 to supersonic. Ryan design studies show many configurations with various engine and fan arrangements to accomplish a variety of military missions at supersonic speed. Engines can be matched to the aircraft mission conditions rather than for the high thrust usually required for vertical flight operations. The vertifan principle, with its 300% augmentation of basic thrust, provides real operational efficiency in a high-performance VSTOL. It means greater payload, longer range, reduced logistic support, and lower fuel requirements. The pilot makes a smooth reconversion from wing-supported to fan-supported flight without change of altitude. The pneumatic exhaust gas coupling between horizontal flight jet engines and the vertical flight lift fans in the wings eliminates the complexity of mechanical power transmission. The gear comes down and locks, preparatory to the vertical landing. Lift fan aircraft draw on the best features of jet engines for cruise and fans or rotors for vertical takeoff and hovering. Other VSTOLs must carry multiple special lift engines or engines far larger, more fuel-hungry than necessary for normal cruising flight. Obviously, the plane which can do the VTO job with the least power offers the greatest advantage. Setting the pace for world progress in VSTOL, the potential of the Ryan vertifan concept, as seen in the remarkable performance of the XV-5A, appears as limitless as aviation's own future.